Hello, friends. The most amazing thing about our universe might be how incredibly big it is, but this hugeness can also be very disappointing. Let me explain why. Imagine we use our best telescopes today and find another planet like Earth in a faraway galaxy, a planet where humans could live. Sounds exciting, right? Well, here's the problem: it would take hundreds of years for us to get there. Let's look at some real numbers. Our Earth is in something called the Milky Way galaxy. The closest galaxy to us is called Andromeda Galaxy. It's about 2.5 million light years away from Earth. If we sent a spaceship there at our usual speed of 28,000 kilometers per hour, it would take 94.5 billion years to reach it. Even if we could somehow travel at the speed of light, it would still take 2.5 million years to get there. This is really disappointing. What's the point of finding all these amazing planets if we can never visit them? But what if there was a shortcut? What if we could travel millions of light years in just a few months? These shortcuts, my friends, are called wormholes. Remember the 2014 movie Interstellar? It's my favorite space movie, and I love talking about it. In this film, when Cooper and his team leave Earth to find other planets where humans can live, they travel to another galaxy through something called a wormhole. They cross from one galaxy to another in just minutes. In the movie, NASA discovered this wormhole near Saturn. It's mentioned many times in the film because it plays a very important role in the story. But here's the cool part. Wormholes aren't just science fiction. They're based on real science. What are wormholes exactly? And how can we use them? To understand this, we need to go back to Albert Einstein and his famous theory of relativity. I've talked about this before when explaining black holes. Now let's go a little deeper. When Einstein wrote his theory, he created a set of math equations called Einstein's field equations. He first shared these with the world on November 25, 1915, when he presented his paper to scientists in Berlin, Germany. These equations are made up of 10 very complicated math problems, but we can write them all as one big equation. Don't worry, I won't show you all the math because it's super complicated and would make your head spin. These equations basically tell us how matter and energy bend something called space-time. Einstein said we should imagine space-time like a big, stretchy mesh or trampoline. When you put heavy objects on this mesh, it bends down because of the weight. Space-time works the same way. Big planets and stars make the space-time mesh curve around them. The heavier the object, the more the mesh bends. Here's something interesting. Einstein himself couldn't solve his own equations completely. He only found one solution for a special case. The first person to solve Einstein's equations was a scientist named Carl Schwarzschild in 1916. He figured out exactly how much space-time bends around a single ball of matter. Schwarzschild's work helped scientists understand what would happen if this matter became incredibly dense. The space-time curve would wrap so tightly around it that this area would get cut off from the rest of the universe. This gave us the idea of black holes. Scientists proved black holes could exist about 100 years ago. But we didn't actually see one until 2019, when we took the first photo of a black hole. So basically, what I want to say is that one solution to these equations was black holes. We already knew black holes could exist about 100 years before we actually found them. And the thing is, friends, another solution to these equations is wormholes. You might wonder how one equation can have two different answers. Well, you remember solving simple math problems in school? This equation also has two solutions, x equals 2 and x equals 3. Both are correct. Einstein's equations are much more complicated. Actually, there can be many different solutions to them. Wormholes are one such solution, and the scientific name for wormholes is the Einstein-Rosen bridge. This name comes from Albert Einstein and his assistant Nathan Rosen, who worked together and came up with this solution in 1935. So it's very easy to understand wormholes. They're basically shortcuts that connect two different points in space-time. First, I'll explain this in 2 dimensions so it's easy for you to understand. Look at this paper. There are 2 points, A and B, on this paper. If you want to go from pointer to point B using the shortest route, which route would it be? The straight line that connects A and B. There can be no shorter route in 2 dimensions except the straight line connecting both points, but if this 2-dimensional mesh is bent into 3 dimensions, you'll see new paths appear. I've bent A and B in such a way that if you want to choose the shortest path to go from A to B, then this distance of just a few millimeters between A and B can be used directly. If I make a path here between these two, literally by poking a pen through, then literally a shortcut has been found to go from A to B, which is much, much shorter compared to the original path. Wormholes are doing the same thing. In our three-dimensional world, we think the shortest way to go from Milky Way galaxy to Andromeda galaxy is 2.5 million light-years long, but if our 3D space is curved or bent into the fourth dimension, then it's possible we can find a shorter, better shortcut. Now, it's very difficult for us to imagine the fourth dimension because we all live in 3 dimensions. But to some extent, you can understand it better if you compare 2 dimensions and 3 dimensions. I'll give you another example. This is a world map. If you want to fly from Delhi to New York, what would be the shortest route? You'd say a straight line connecting Delhi to New York with the flight flying over Africa, but in reality, this would not be the shortest route because you're thinking in 2 dimensions. The shortest route would be to travel over Finland, Sweden, passing by Iceland, and Greenland to reach New York. This looks like a longer route on the flat map, unnecessarily flying to the north. But if you look at it in 3D, it looks obvious that it is the shortest route. In 1957, scientist John Wheeler published a paper on Einstein's Rosen bridges. He compared it with a similar example. He gave an example of an apple and a worm eating that apple. The worm reaches from one side of the apple to the other while eating through the middle. Instead of traveling on the surface of the apple like our airplanes travel around Earth's surface, the worm travels a shorter distance by going through the middle dot. In a way, it has taken a shortcut in space-time. Wheeler named this a wormhole. And this is where the word wormhole came from. When you search for wormholes on the internet, you see many diagrams. Basically the same thing I did with the paper. 2 points connected through a hole. Here, it's imagined that we have a space-time mesh, and there's an object with extremely strong gravity. So strong that the curvature of space-time is bent so much that it has poked through to the other side. The space-time mesh has folded on itself, just like I folded that paper. And this wormhole has become a shortcut to travel from one galaxy to another. But in all these pictures, the problem is with the dimensions. We try to show a wormhole in 2 dimensions. But as I said, wormholes work. In 3D to 4D. In reality, if a wormhole exists, it will look like a round ball. There are very interesting websites where you can see how wormholes will actually look if they really exist. A ball-like shape, whereas you go inside, everything you see around you is curved. And if you turn around and look, Earth is moving away from you. And everything will look circular. That's why the wormhole shown in the interstellar film is shown in a very realistic way. Here, it's important to mention that wormholes are still just a theoretical idea. They've been proven using math as a solution to Einstein's field equations. In movies, scientists have tried to show us what they might look like. Many theories have been formed about them, but practically no one has seen a real wormhole yet. Scientists don't know whether wormholes really exist or not. But if wormholes exist, they will work as time machines too. Just imagine being able to travel millions of light years in a few minutes. This means you can reach there even before light. If light didn't reach there, then basically you have jumped from one place in time to another. Now it's a different question. That if wormholes do exist, can humans really travel through them? If wormholes are real, what problems come with them? The first question is, how will the opening of the wormhole be created? We will need extremely heavy gravitational force here. Where can we find this gravitational force? If you have seen my old space videos, you can guess what the answer to this question is. A black hole. Einstein and his assistant Rosen thought that only black holes can have such gravitational force that they can open up these tunnels of wormholes. Everything is attracted to black holes. Everything will be attracted to it and will flow through this wormhole through this tunnel. But the next question is, what will be on the other side of this tunnel? If there is a black hole on the other side, then there will be no way to get out of this tunnel. You will be trapped inside this tunnel. Basically, in that case, this wormhole will not be a tunnel to go from one place to another, but rather it will be a trap. There should be something on the other side, which is the opposite of a black hole. In every sense, something which is as powerful as black holes, but works in the exact opposite way. Something that instead of attracting things towards itself, sends things away from itself, so that an exit point can be created. And here enters in our story the white holes. Once again, white holes is a concept that has been proven using math by Einstein's field equations. Apart from black holes and wormholes, white holes are another solution to these field equations. What are these white holes? Like white is the opposite of black, a white hole is the opposite of a black hole in every sense. Like in a black hole, no light can escape once it is trapped inside. On the other hand, in a white hole, no light can enter. It can only come out from it. This means that the white hole will be extremely bright and white in color. Russian scientist Igor Novikov was the first person to use the term white hole in 1964. According to scientists, a white hole is basically a time reversal of a black hole. Like the event horizon of a black hole is a point of no return. Once it is crossed, nothing can escape from it. Similarly, the event horizon of a white hole is a boundary of no entry. Nothing can go beyond that point. The objects inside the white hole can go outside and interact with the outside world, but they cannot go back inside. Even though this is a solution to Einstein's theory, no one actually knows how white holes will form in reality. I explained how black holes form in my video about black holes when a star collapses on itself. But what can be the opposite of this? So, can white holes exist or not? This is still being discussed among scientists today. Some scientists believe that when Big Bang happened and the universe was formed, at that moment of creation, everything must have come out from a gigantic white hole. Another theory is based on Stephen Hawking's idea. Stephen Hawking said that a black hole will eventually disappear when radiation keeps leaking from it. Black holes are not eternal. They evaporate away at an increasing rate until they vanish in a gigantic explosion. But when a black hole dies, what will happen to the information and matter inside it? There's a basic rule in science which says that no information can be lost. It is called the no-hiding theorem. According to the no-hiding theorem, even if any information disappears from a system, it would still be existing somewhere or the other in the universe. So if all this matter and information is being sucked into a black hole, it will be spit out after the death of the black hole. And this is likely happening through a white hole. Based on this argument, many scientists say that a white hole forms when a black hole dies, but till now, we do not have any solid information about how a black hole dies. On the other hand, some scientists argue that it's impossible for a white hole to exist because it breaks the second law of thermodynamics. As you must have studied in school, the second law of thermodynamics says that entropy in any system cannot be reduced. Take this paper as an example. If I tear this paper, after the paper is torn, the entropy is simply increasing. Now, it is not possible to join it again in the same way. The way a paper shredding machine shreds the paper, which increases the entropy. In the same way, black holes shred everything in the universe. Black holes swallow entire planets and stars, and only radiation is left behind. This increases the entropy in the universe. But if you try to imagine that it is happening in reverse, with entropy decreasing, this is not possible. And if white holes do exist, then basically this is what they will try to do. So according to this logic, perhaps they cannot exist, but despite this, some scientists believe that not only do white holes exist, but that in 2006, scientists saw a white hole. On June 14, 2006, a space satellite named Neil Gehrels Swift Observatory captured something strange. Scientists saw an explosion of white light which suddenly disappeared. This event was called GRB 060614. It was a gamma-ray burst. Gamma-ray bursts are basically highly energetic explosions observed in distant galaxies. Usually, these events occur when a black hole swallows a big star. You can see very bright explosions of light, but in this case, no evidence of a star was found. So it was thought that this was an observation of a white hole. Since then, we have not seen such an event again. And that's why till now, white holes is only a theoretical concept, but the thing to note here is that black holes were also theoretical at one time. But then one day, they were practically proven. So it's possible that in the future the same will happen with white holes. The same thing can be said about wormholes. Friends, it's possible that they can be proven in the future, but even if their existence is proven, scientists still doubt whether humans will be able to travel through them or not. The most interesting news about wormholes' existence is from 2015. When scientists created a magnetic wormhole in a laboratory. So till now, we were talking about wormholes in terms of gravitational force, But if we talk about magnetic force, scientists have already been successful in creating wormholes. What does this mean? There are two ends of a magnet, a north pole and a south pole. We know that the two ends always stay together. Even if you break a magnet into two pieces, both pieces will still have both poles. Scientists use some special materials and achieve something by separating the two poles of the magnets and put an invisible gap between the two. Basically, the magnetic field of one magnet went inside one end of the wormhole and came out from the other end. You can see its picture here. The left image shows a device which was created by the scientists which separated the two poles of the magnet. So this device is basically working as a wormhole for the magnetic field. We can see this device with our eyes, but if you look at the magnetic fields in the right picture, you will see that on one side, there is a pole of the magnet, and on the other side, the other pole is separated and at a distance. Like in space, a wormhole works by bending the space-time curvature. Here, this wormhole bent the magnetic field. To make this magnetic wormhole, a special material was used known as yttrium barium copper oxide, and it was kept in a liquid nitrogen bath to conduct this experiment. Finally, friends, I would like to say that even if the existence of wormholes is not proven in the future, it does not mean that we cannot find other ways to travel faster than light. In theory, several other solutions are proposed. One is Alcubierre drive. It was proposed in 1994 by physicist Miguel Alcubierre. The idea here is that there will be a spacecraft which will be able to travel at a speed faster than light. But how will it be able to do that? By contracting the space-time curvature in front and expanding the space-time curvature in the back. This is also a theoretical solution to Einstein's field equation presented by Alcubierre drive. It will be very interesting to see the other solutions proposed for these field equations and what practical things can be made from them. For now, if you like this explanation and if you want to know more about such space topics, you can check out more videos on black holes. Thank you very much.